Hello, and thank you for joining our webinar today that we have titled Tips and Tricks for a Long Product Life, Preventing and Investigating Microbial Spoilage. I'd like to start by giving a brief introduction to our featured presenters. First, we have Dr. David Legan. He is the Director of Science for Eurofins Microbiology. He provides key technical support throughout our entire US network of Eurofins labs. So David holds a PhD from the University of Reading in the UK and has an extensive history of spoilage investigations and preservation system development dating back to 1985 in third-party labs as well as well-known CPG companies. So today, David will be providing the background and basis for the core principles of food spoilage. We are also joined by Patricia Quinn, who is the Analytical Services and Project Manager for real-time and microbiological studies and co-manager for all other accelerated studies working with the National Food Lab of Eurofins. So Patricia and her team handle dozens of investigations per year. Today, Patty will be giving us context and application of the principles with case study examples and an overview of the investigation practice. Okay, so with that, Patty, I'm going to hand this over to you to begin our conversation.
All right, so today we're going to be going through the shelf life background and theory, of course, spoilage examples and some case studies, and introduce formulating for shelf life on your product, and also illustrating spoilage investigations and our diagnosis process. All right, so shelf life and spoilage, background and theory. Of course, you know, we all encounter spoilage at some point in our lives. We've opened up a refrigerator, or we have seen something maybe on a shelf where, you know, you could tell it wasn't something that you would want to be eating. But I really want to focus today on what is spoilage in the sense of you know, what it means in our industry. And it is the microbiological, chemical, and physical changes within a food product which lead to a reduction of acceptability to a consumer. In our industry, in the food industry, it's certainly a priority to keep our products appealing to consumers and customers while also adhering to quality expectations within our manufacturing process, and also while competing industriously with other brands. The USDA actually ranks spoilage along with inadequate climate control and storage and inadequate protection from pests as a leading cause of food loss, also known as shrink, in the global food supply chain. Now, this adds up to literally billions of pounds of food, and of course, then consequently dollars in loss, in product loss and revenue loss. So our goal then, of course, is to prevent early or pre-target shelf life spoilage to maximize consumer satisfaction, maintain our brand integrity, and save money in so many different ways. So I'm going to jump right into one of our interesting case studies that came through the lab. One of our clients had reached out to us. They manufacture sauces, and they had consumer complaints. They had some complaints of a sour, or what was repeatedly described as a funky off flavor in a finished product barbecue sauce. So we looked at some of the symptoms and the signs of spoilage that were being reported by the consumers in the complaints, and looked at the product as a whole, of course, and we decided to move forward with a custom spoilage investigation. We performed screening for all of what we would have deemed usual suspects for this type of product. But interestingly, only the anaerobic plate count had recovered any growth. So anaerobic bacterial cultures, those are bacteria that grow in conditions that lack oxygen. we took the cultures and we had them sequenced. Now the result, when it came back, was pretty surprising. It was not expected at all. The bacteria that we found is called Cutibacterium acnes. And if your red flags are going off, that's because you're probably associating this with the word acne, and you would be right. This is acne bacteria. It is part of the flora present on most healthy adult human skin. And it produces these short chain fatty acids, in particular propionic acid, and that is actually what was producing that funky off flavor. Now, this strongly suggests a failure in the GMP or good manufacturing process, which is one of the hurdles that we'll discuss today.
So as we begin to think about what is it that limits shelf life, I'm having the same clicking issue. Patricia has already indicated a number of factors that affect spoilage or that define the end of product shelf life. Sensory qualities are affected by physical and chemical changes, and we're not going to discuss those anymore today. We really will be focusing our emphasis on microbiological changes, and we tend to recognize those through things like gas production, giving us a bubbly product or a blown package like the one on the image here, strange odors, alcoholic, solventy, kerosene odors, visible mold, visible slime, that kind of thing. And the rate at which that spoilage occurs is driven by a number of factors, both intrinsic to the product and extrinsic factors. Factors intrinsic to the product are things like water activity, pH and acidity, preservatives and other inhibitors within the product, and then to a lesser extent product structure can play into this, and availability of nutrients for microbial growth. Most of what we talk about today will focus in this area, so I'll just mention at this point that extrinsic factors can be used to influence product shelf life. So thinking about refrigeration for extending shelf life, controlling humidity around a product can help, and we have the possibility to modify the atmosphere around a product. If we reduce the oxygen content of a pack, if we increase the carbon dioxide content of a pack, that can give us some antimicrobial activity. We're not going to spend really any more time on these things today because they bring in a layer of complexity that we really don't have time to address. Now, as we think about these factors and how they interact, there are several different mental models that have been used within the industry. The first of these was presented by Felix Leistner back in 1976 and is thought of as the hurdles concept and well known in food science circles. The idea here is that each time you add a new factor, be it water activity or pH or processing or a preservative, each of these factors takes some energy away from the microorganism. After it's jumped the factor, it becomes a little more tired until eventually it can't jump anymore. I personally have always struggled with this mental model, first of all, because it looks more like a collection of boiled eggs than it looks like hurdles. And secondly, because it doesn't connect in my mind with this notion of hurdles or barriers adding to one another. So I've always thought in terms of a high jump or a pole vault model, where literally each factor that you add literally raises the bar, making it harder and harder to clear until eventually the bar raises so high that in this example, your athlete, or in the food product example, your microorganism is unable literally to clear the bar. And at that point, you have controlled spoilage. I published this a couple of years ago with a co-author in a book chapter. And I will say at this point that my original mental model was a brick wall. so that when you finally make the wall too high, it gets extremely painful for the athlete that fails to clear it. My co-author is much kinder than I am, so we settled on the bar analogy. Now, in my mind, the first and most important single factor in any food product is water activity. The water activity gives us a measure of the availability of water and how that can make it more or less easy for microorganisms to grow. Essentially, all life needs water, and the more available water is, the better things will grow. Water activity is defined as the vapor pressure of water surrounding the product in a sealed system, divided by the vapor pressure of pure water at the same temperature. And we don't have to really give any further thought to the definition. What we should pay attention to is that it's expressed as a decimal. So on a range of 0 to 1, the larger that number is, the more available water is, and the shorter you could expect the product shelf life to be, other things being equal. Now, because it's measured as the relative humidity around a product in a sealed chamber, you will also often see that's presented as a percentage number. So it's the same thing. You multiply water activity by 100 and you get percentage ERH. So as we talk today, if we go backwards and forwards between 0.8 AW, 80% ERH, it means the same thing. Water activity affects very many different spoilage elements within a food product. Both the physical and chemical elements like browning reactions and lipid oxidation that we're not going to consider any further, and the microbial growth. So for today, we're really most interested in the bottom right-hand corner of this chart, which is illustrating to us that as the water activity is reduced, the microbial growth rate rapidly reduces, and eventually we reach a point where neither bacteria, yeast, nor molds are able to grow, and at that point we have a totally shelf-stable product from a microbial point of view. As we reduce water activity, there are a couple of other effects that it's worth paying attention to. So looking at the first column in this chart, you can see that as we reduce the water activity, we progressively get to the minimum for growth of more and more different species. And these are all pathogenic bacteria, so we're progressively reducing the pathogen risk as we go down this water activity table. Eventually, at an AW of 0.86, we reach the minimum for growth of Staphylococcus aureus, and below that, we don't need to consider growth of pathogens. We should, though, remember that many of them can survive for extended periods of time at low water activity. So we certainly need processes and procedures in place to make sure that they're not present, but we don't have to think about their growth. And then in the right-hand two columns of the chart, you see a similar thing, which is as we reduce the water activity, we progressively reach the minimum for growth of different molds and yeasts, so they no longer become spoilage issues. And when we're down in the 0.6-ish range, we just have two organisms left, Zygosaccharomyces rooksii, the yeast, Xeromyces bisporus, the mold, and you could consider these the water activity gold medalists of the microbial world. Below 0.6 AW, we expect no further microbial growth. And that leads us into the first of Patricia's case studies.
Yeah, so this case study definitely ties right into this water activity as being a limiting factor. So we had a client reach out. They produce pet food and pet treats, and they had received some consumer complaints that there was visible mold growth in these packages where the treats had been opened for a couple of days. So we had received some of those samples, and there was there was mold growth all over every one of the treats in nearly every package that that we had received. So we decided to analyze the samples from several of these opened packages, as well as some unopened packages to see if there would be a difference between, the stuff that had been opened and exposed to air and some that had been still sitting on the shelf. So what we found was that there was still a pretty high mold count on the unopened bag of treats. Well, of course, we had visible mold growth on the opened bags of treats, and the plates for the opened bags were completely overgrown with mold. The plates for the unopened bags of treats still had pretty, I would say, relatively high counts, but not anywhere near as that lawn of growth as we observed on the opened bags. The colony appearance was similar on all of the growth across all of the plates and across the growth on the actual physical treats. So we had cultures sequenced, and our ID came back as a mold called Penicillium crustosum. This is a common agent of fungal spoilage as it has a wide range of tolerance for pH, temperature, and water activity. Unfortunately, considering the situation, it also does have the ability to create mycotoxins that would be considered a veterinary concern. So one thing that we wanted to look at once we had a comprehensive data set was, why did the opened bag of treats yield such high numbers of mold in comparison to the unopened bags? Well, we decided to proceed with some additional chemical testing, in particular water activity in this case. And the water activity of the unopened treat bags had ranged from between 0.71 and 0.78, while the water activity of the opened bags was all greater than 0.80. So the treats themselves are made of beef and some other ingredients which were a soft texture. What we concluded was that the treats were absorbing moisture from the environment upon opening the bag, and which led to this excess of mold growth. So we talked to our client after we did some brainstorming, and ultimately the recommendation would be lower the water activity to under 0.70, harden the treats so that they aren't so porous and cannot absorb all of that humidity from the ambient air upon opening of the bags. Well, they went back to the drawing board, and we received some subsequent samples after reformulation, and they had no mold growth at all, and the water activity had been lowered down to 0.251 and 0.315. So we were able to help them troubleshoot the issue, and no doggies were harmed.
So the next factor that we're going to consider is pH and acidity. These are very connected concepts. pH itself is a direct measure of acidity and alkalinity on a scale of 0 to 14. 0 is the most acidic, 14 is the most alkaline, 7 is neutral. An important piece of the microbial connection here is, as we get to more extreme pH values, either acidic or alkaline, the number of microorganisms able to grow reduces, and the growth rate of those that are remaining is also reduced. But for the most part, foods are neutral to acidic, and so we'll focus our thoughts in the acidic range. And a very traditional preservation technology is pickling, either by lactic acid fermentation or by direct acidification of the product with an acid such as vinegar. This technology works primarily by giving us an extremely low pH, but also some of the organic acids have an intrinsic antimicrobial activity of their own. So that is something to keep in mind. Acetic and lactic acids have a little bit more antimicrobial activity than phosphoric acid. The choice of acid, if we have a choice, is usually driven by compatibility with the flavor profile of the product that we're trying to make. And an additional thought to keep in mind at this point is that there are many preservatives based on organic acids, and their activity is promoted by reducing pH. We'll look at those in a minute, but first we'll just take a quick look at how microbial growth is affected by pH. And you'll see here that bacteria have, in general, the narrowest pH range for growth. Yeasts and molds, in general, have a wider pH range than growth for growth than bacteria, and certainly the ability in most cases to grow to lower pHs. So as we get into acidic and acidified foods, yeast and molds are more likely to be our primary causes of spoilage, though there are a couple of bacteria that can be a concern in specific circumstances. And then if we think about the organic acid preservatives, these are things like propionic acid, sorbic acid, benzoic acid, and their salts, which are used really as additives at low concentrations, certainly below the 3,000 part per million range, and in some regulatory jurisdictions, much lower than that. All of these become more effective as the pH is reduced because we drive the acid or the salt into the undissociated form, and that has an ability to go through microbial membranes and then cause inhibition within the cells. They're arranged here really in order of pH effectiveness from high to low. So propionic acid and its salts we tend to see in bakery products which are nearly neutral pH. Sorbic acid tends to come in through things like salad dressings and also in bakery products because it has a wide range. Benzoic acid tends to focus on acidic products like salad dressings and acidic beverages. So rather than a case study here, we'll pick a couple of literature examples to look at to illustrate some particular points. The first case study, or the first literature example, I should say, was published a couple of years ago in a model light salad dressing. The formula was predominantly oil, acid, water, sugar, and some minor ingredients, and the system was inoculated with Zygosaccharomyces parabelii, a relatively newly recognized close relative of Zygosaccharomyces bailii. Now, because this was a light dressing, the authors of this study knew that it would not be stable at room temperature. That wasn't the primary focus of the study, but still we can see here the effect of temperature. Spoilage, growth of the organism and spoilage was much quicker at 25 degrees C than at 10, and then at 4 we had no growth and stability. The more important point to make on this slide is that in all cases acetic acid gave the greatest inhibition of growth of the acids tested. So acetic was more inhibitory than lactic, which was more inhibitory than gluconic acid, even when gluconic acid was used at pH 3.2, whereas the other two acids were at pH 4.2. So when formulating acidic products, choice of acid matters to the extent that you can do it within the flavor profile. You want to choose a more antimicrobial acid. And the second example really was a model study that came out of one of my groups many years ago, looking at stability of a salad dressing, looking at the total salt and sugar content and the total undissociated acid content of the system. Undissociated acid is a function of both the total acid concentration and the pH. At lower pH, we have more undissociated acid. And I think what comes out from this chart is that at low salt and sugar concentrations, low undissociated acid concentration, we're expecting very quick growth, in this case at 30 degrees C in a system inoculated with Z. baileyii. As we increase the concentrations of salt and sugar or increase the concentrations of undissociated acid, we drive through this series of contour lines of increasing time to growth. So we progressively go through 20, 40, 60, and so on days up until we exceed 120 days, which was in this study sort of practical limit. Once we have 120 days of stability, we would feel okay with that as a model product. And what I think you can see from this chart is that actually there are very many ways along this boundary line that we can get to that stable endpoint, either by focusing on the salt and sugar content, or by focusing on the undissociated acid content, or by using a balance of the two. And that, again, all really will play into what you want the flavor profile of the product to be as you achieve the stability that you need. Moving past water activity, moving past pH and acidity, and we gave a brief look at acidic food preservatives. There are a number of other antimicrobial compounds that show up in foods in particular situations. So we tend to find nitrites in cured meats. They are in fact the kind of defining ingredient. It's the nitrites, even at very low concentration, that give us the pink color that we expect from a ham or a pastrami. And nitrites provide an antibacterial activity within the product. Things like sulfites can be used to inhibit growth of yeast and molds, and we see those coming to be used in things like dried fruits and some wines. There is a little watch out there that they give intolerances or allergic reactions in some people. Then we have some natural antimicrobial options, things like niacin, which is a natural antibacterial compound, or natamycin, which is a natural mold inhibitor. And all of these options play into formulation in different circumstances. But they don't necessarily all play into consumer preferences. And what we've seen over the years is more and more preference from consumers for natural, which would be fine with niacin or natamycin, and clean label or friendly label, or things that I can pronounce, in which case maybe the natural antimicrobial options are not so friendly. And we'll see a number of ingredients used, things like cultured sugar, cultured celery, and they are ways to provide some of the active ingredients in a way that is derived from materials that consumers would recognize and accept. And then we get to some rather less common limiting factors. The first of these, which is seen in a number of circumstances, probably the place that we notice it most is in butter, is structure. And that plays into butter because butter is a water in fat emulsion. And the water droplets within the portion of butter are very, very small. So even if there is a microorganism in a water droplet, it's physically constrained by how much it can grow. And that means that butter is much more stable than the cream from which it's derived. If we further go on and salt the butter, even at relatively low concentration, 1 to 1.5% salt concentration, what we find is that the salt partitions into the water, That gives us a high salt on water concentration, a reduced water activity, and that further constrains bacterial growth. So there are some circumstances where we can play with structure and deliberately have an effect on shelf life. And then we get into some really interesting situations. So nutrient limitation can definitely reduce microbial growth. And there are some natural systems around, such as the overtransferrin in egg white, the lactoferrin in milk, that are there evolutionarily to chelate iron in the system, making iron unavailable for microbial growth. And actually, in the sense of eggs, provide a pretty powerful protection against microbial invasion. Now, when we're formulating a food product, bringing in multiple different ingredients from many different locations and sources, it's very hard to deliberately formulate for nutrient limitation. But we can be surprised and find that we have it where we may not expect it. And that leads us into the next case study.
All right, sir. So in this case study, we had a cheese manufacturer reach out to us. They were experiencing a pretty severe bloating, I mean like pack bloating, like really big, bloating and ropiness. And ropiness is something that we kind of use to describe a slimy texture consistency in a modified atmospheric packaged shredded queso. So we proceeded with a spoilage investigation, and our primary suspects in this case were lactic acid bacteria, leuconostoc, coliforms, psychotrophic bacteria, which are bacteria that thrive in refrigerated conditions, and Clostridium species. Well, the interesting thing about this particular case is that the shredded queso was all coming from the same cheese provider, but there were actually 3 different brands where the cheese was being packaged at 3 different co-packers under 3 different brands. So we wanted to compare against all three of these different brands, and what we found was that one was exhibiting that really high gassing, super bloated packs. We had one brand that was experiencing low gassing and one that had not experienced any gassing. Well, after the testing, we're reading the plates and found that the coliforms, the lactic acid bacteria, leuconostoc, psychotrophic plate count, they all exhibited very high counts. There was high contamination across all 3 brands. But why was there high gassing in one of the brands while not experiencing that level of gassing in the other brands that was being used, even though the counts were high across all 3? Well, looking at the ingredients, the low gassing and the no gassing brands were using cellulose as an anti-caking agent, where the high gassing brand was using potato starch as the anti-caking agent. Consumption of potato starch by lactic acid bacteria can lead to additional fermentation, which was ultimately what was causing that excessive bloating and gassing in that one brand. So as far as coming to a solution or a resolution with the client, first you got to fix the problem. They had a massive cleaning endeavor at the cheese plant itself, and the one brand or co-packer, they actually switched out the potato starch for cellulose as their anti-caking agent. To monitor this as an ongoing potential for an issue, they beefed up their testing protocols. So they sent in a bunch of sanitation swabs and they continue to do so. And they are monitoring for coliforms and lactic acid bacteria. They're also monitoring the product itself routinely for coliforms, lactic acid bacteria, and leuconostoc. Apologies, my clicking is a little slow there. So ultimately, all of these case studies and everything that David has also outlined today, these are tools to really help us not only formulate our products for shelf life, but also can help us with these investigations and diagnosis when things go wrong. So investigation and remediation. When something goes wrong or you're getting consumer complaints about a product or you suspect that there's been contamination, working with a laboratory is the first step in the right direction for an actual investigation. You'll want to discuss symptoms and product factors with your laboratory and collect samples for analysis. The laboratory itself probably wouldn't collect those samples, but certainly should be able to provide you with successful submission instructions. At that point, performing of microbiological and or chemical analyses such as water activity and pH can help us identify the cause of spoilage. And lastly, you'll want to discuss all of the findings and all of the data in a comprehensive manner with the team that is supporting you. So some of the things that you'll discuss with the team right off the bat are the signs and symptoms of the spoilage that is occurring in your product. Of course, these are some factors that you'll go over right off the bat. So appearance, texture, odor, and flavor, these are called organoleptic qualities. And we want to make note that while, yes, we'll make note of the appearance, the texture, and maybe even some odor in the lab, we're not going to ever, and we wouldn't encourage anyone to deliberately taste any spoiled products. And you'll want to also be careful smelling a moldy product, yourself, especially as those spores can be airborne. Now we're going to ask a lot of questions, right? Or the lab team that you would be working with, they would ask a lot of questions off the bat to try to really kind of limit and focus in on what I was referring to earlier as our primary suspects. The reason for this is that when we narrow down the investigation to from the symptoms to the factors of your product and how it's packaged, how it's stored, what was the consumer's feedback, well, that can help us narrow down those tests that we would be considering prior to any ID tests that we would perform. So don't get irritated. I promise all of those questions are to help design a study that is catered directly to your product, and also so you aren't just spending a lot of money on something where we could probably have narrowed it down for you. So as far as post-diagnosis considerations, once you've had a study conducted with a laboratory, you'd want to discuss those immediate and ongoing solutions with a microbiologist if it's microbial spoilage that you've been experiencing, or a chemist if it's something other than that. Your lab should be able to provide you with pretty intensive environmental monitoring program support. And this could also include a hotspot diagnosis or harborage site investigation, where someone with a lot of knowledge in manufacturing and microbiology and in the industry could come on site to your facility to perform harborage site investigations to look for sources of contamination and help you diagnose some of those hotspots that might be in your facility. Another thing that you could work with your laboratory is validating your kill step processes to make sure that they're working as intended. Yet another solution to consider is reviewing your product design for prevention of premature spoilage and premature loss of shelf life. One option is considering a spoilage challenge study after your product has been reformulated or during initial product formulation, where the lab would actually take your product, inoculate it with a target spoilage organism of concern for your product, and see how that spoilage organism either thrives or dies off over a given period of time.
So as we just wrap up the thoughts on product spoilage and factors affecting the rate thereof, thinking how that plays into product design, we've really focused to this point on formulating with intrinsic factors to maximize product stability. We've looked at how interactions between factors can be important. We've hinted at how we can use models or simply trial and error to optimize a formula for the shelf life that we're looking for. We've indicated that extrinsic factors such as temperature and pack atmosphere can support that formulation decision, but we didn't go into that because of the time available to us today. So I guess the final thought really on this is that ultimately it's the consumer experience, it's the eating quality that drives repeat purchase of a food product. And that provides a key constraint whenever we're trying to think about product shelf life. We can modify all of these factors within some constraints. But eventually, once we push them too far in any direction, we no longer have the food product quality that we wanted to provide or that the consumer wants to buy. There are circumstances where we can't say ever that you can have a product with an indefinite shelf life, but certainly within the theoretical possibilities for any particular type of product, you can get close to the theoretical limit. Yeah, we go, Scott.
Okay, thank you so much, David and Patricia. Excellent overview there. I'd like to come back in as we're closing up here for a quick plug in a way for our next webinar. So we talked a lot today about our principles and practice of spoilage investigations. One of the things that we hinted at, as was mentioned throughout, is perhaps what could be done about that. So in a follow-up webinar with the National Food Lab, we're going to talk a little bit more about formulation approaches to improve microbial stability. So that webinar, as you can see here, we'll get into the ever-changing consumer requirements, formulation strategies to help ensure safety. The presentation covers topics around food safety product categories, impact of ingredients required to improve stability on product acceptance. Click on to the next slide here. So our presentation today did go into a high-level overview on the shelf life and product spoilage. I wanted to provide another reference here for a little more information should you choose to dive a little deeper into our white paper on the topic that covers a little bit of what we talked about today and providing a little bit more depth into the details. And again, below here, you also see a QR code if you choose to scan to register for that webinar that I just mentioned on the previous slide. And finally, at the bottom, you can see some contact information for both David and Patricia, should you have any direct questions to reach out to them following the webinar. So with that, I'm going to switch over and have a look at the questions that came in, and we have about 10 to 15 minutes here to discuss any of the Q&A. Okay, so I suppose I'll start off with one of my questions. So we went quickly over the extrinsic factors, but one of Patricia's case studies was about a product in modified atmosphere packaging. Can we say more about the modified atmosphere packaging or other packaging approaches to solving some of these problems?
We can always say more, Scott.
Well,
But
please
before
do.
I do, I have to make sure I'm unmuted.
Yes.
Yeah, so I think the primary thing going on in modified atmosphere packaging is reducing the oxygen availability. So there are two broad approaches to that, depending on the nature of the product. So the simplest way to reduce the availability of oxygen in a product is a vacuum package, which you'll see, raw meats are often vacuum packaged, ready-to-eat meats are often vacuum packaged. Those are products that don't crush very easily, so you can squish all of the air out of the pack. For more fragile products, vacuum packaging really doesn't necessarily work. So we would, for example, replace the oxygen with nitrogen or some inert gas, and then the effect that you're getting is only down to the reduction in oxygen concentration. That can be effective at reducing the growth rate of mold. That's what it's often used for. We can get a bigger effect by substituting carbon dioxide into the package. CO2 itself is actively antimicrobial against very many organisms, but it does tend to dissolve into any water that's in the product. So if we go to 100% CO2 atmosphere, we could expect very quickly all of that to be absorbed into the product. The package would collapse as a result. And again, with a delicate product, you would damage the product. So we would tend to use CO2 at some ratio with a balanced gas such as nitrogen, 60-40 nitrogen CO2 or 40-60 nitrogen CO2 are often used depending on how collapsible the product is. And then the final thing to keep in mind is that we're paying for expensive gases, and so we need a film that's going to retain them. Those high barrier films tend to be more expensive, but then that just becomes an overall cost optimization question around how long we want the shelf life to be, what we're trying to protect against, what the consumer's willing to pay, and you get into the whole business decision and move away from the science at that point.
That makes sense. Thank you very much. Okay, moving on to another question then. When I'm developing a new product, how can I estimate its shelf life and know that it meets the project brief?
Well, I think Patricia began to hint at this on one of the later slides in terms of, she mentioned challenge studies. But before we get to that stage, I think there are a number of other things that we can look at. First of all, looking at similar products in the marketplace, what's a typical expectation? And you would expect the typical shelf life expectation of a cracker to be rather longer than the shelf life expectation of a piece of raw chicken, just to take some extreme examples. And there are many players in the market, and they're all collectively very smart. So it's hard to get in any particular category much beyond the market leader. So that would be kind of one baseline estimate. The next thing that you can do is there are a number of food safety models freely available through an online resource called Combase that was developed multinationally many years ago, and that will give some ability to estimate pathogen growth rate, make sure that we're into a safe space. There are also literature examples for many different kinds of products where there are published models that become available to use to help you estimate for a particular system. Get to a real formulation or a collection of real formulations, and that's where, once we're in a space where we believe we may be close to having something that gives us the sensory qualities we want, and from all of our estimation might be in the right range, then we would move into a challenge study where we would formulate the product, challenge it with the most likely spoilage organisms by inoculation, and then store it in likely or conditions that we believe it's likely to experience in the marketplace, and then monitor for that microbial growth, whether that be looking visually for the appearance of molds, doing counting studies to see what's happening to bacterial growth. So it's kind of a cascade of activities that we would be involved in.
That makes sense. Okay. Well, I suppose we're at the point where we will wrap up our webinar today. So again, thank you all for attending.
Absolutely.
Thank you both for presenting. And we'll talk soon. Thank you very much.
Everyone.
Thank you. Take care.
Bye-bye.